Hello, my name is Vladislav Shpilyovoy. Here I talk about Tarantool release 2.6, where some of the most anticipated features were introduced. Synchronous Replication and Transaction Manager for memtx engine. My talk follows the plan on the slide. Firstly, I will explain how asynchronous replication works and what problems it has. Then I show synchronous replication and what problems it solves with some examples. Then we go to the leader election, its algorithm, and how to use it in Tarantool. Next thing I show is transaction manager and what long existing issues it fixed. In the end, I will shed some light on future of Tarantool in scope of 2.6 and further. Here is how asynchronous replication works. Its core idea is that for a transaction to be successfully committed, it's enough to save it to the local log on disk on the master node. Life cycle of transaction looks like follows. Transaction appears on master, goes to its log on disk, is responded to the client as successful, and its changes become visible. Then it's replicated to other nodes and is written to their logs. A not obvious problem of this schema is that if the master node will die between steps 3 and 5, it leads to data loss because the transaction was responded as successful and was lost after that. So the data is not present on any node and was responded to a client as successful. Here is an example how it happens. Assume there is a bank client who has 100 money. The bank has two nodes in its replica set where account of this client has 100 money. Now the client puts more money into an ATM, plus 50. The ATM sends a request to the replica set to the master node. The request starts a transaction which adds 50 money, and it's written to the log on master, and is responded to the client as successful. The client sees message success on the ATM screen, and in the meantime, the master node starts replication to the second node. And now the master node suddenly dies and can't be recovered anyhow. The second node becomes a new master, but it doesn't have the transaction. Now, if the client will ask how much money he has on the account, he will get a surprising response that his 50 money has just disappeared. Means that with asynchronous replication, the guarantees are almost like without replication. You still can lose data. Another problem with asynchronous replication is the dirty reads. Dirty read is a situation when requests can see not yet committed data. Since the data is not committed, it can be used for anything safely, nor can be shown to the clients. Exactly that can happen if you try to work around synchronous replication on the application level. For example, by trying to wait for a transaction replication after it is committed locally. Because, as I said, it was already committed locally. It means all the newer changes, all the newer requests and transactions, they already see the changes this transaction did. It can lead to interesting bugs because if some other transaction will use the dirty data and the first transaction will be rolled back by a timeout, for instance, and the second transaction will be based on not existing data. Both problems can be properly solved only by using the synchronous replication. As it is opposed to asynchronous replication, it is obvious what it does. It makes the transaction wait for replication before it is committed. So when a transaction of the master node is committed invisible, the application can be sure the data survives even if the master node dies. The transaction lifecycle becomes linear and looks like follows. First, it appears on the master node, then it's written to its local log on disk, then it's replicated to some number of nodes where it's written to their logs. And only now the transaction is marked as committed and its changes become visible. The previously mentioned number of replica nodes needed for a synchronous transaction commit is called quorum. Usually quorum is selected as 50% of nodes plus 1, including the master node too. For example, with 2 nodes, each synchronous transaction must be logged on both to be committed. For 3 nodes, it must be logged on 2. For 5 nodes, on 3, and so on. 50% plus 1 is typically used because it's minimal possible majority, and is related to leader election algorithms, which usually go hand by hand with synchronous replication. But you can use more, even 90% or 100% if you want. 50% plus 1 is just where the guarantees start working. Here is how synchronous replication prevents the data loss, for an example with a bank customer. The client puts 50 money into an ATM, it sends a request to the master node where it starts a transaction. The transaction is written to the log on disk, but is not visible yet. Now it's replicated and written to the replica log. The replica sends an acknowledgement about log write, and the master understands it's time to commit. The master node will write a special commit entry to the log and will send the response to the client that the transaction is finally committed. And now, when the client already got a positive response, the commit entry itself is replicated to the replica asynchronously. But it's fine because loss of the commit entry is not critical. The most important point is the data will survive. If the master node now dies, the second node becomes a new master and the data is not lost. If the client will ask for his balance, he will see the information he expects to see. If all the good parts of synchronous replication would be for free, it would be used always, but it has some shortcomings, making it quite specific. First is that it's slower, because each transaction lifecycle now involves network. It gives additional milliseconds of latency. Also, it's easier to break the cluster to a read-only state, because if some replicas will fail, the master to collect quorum for new transactions and will become basically read-only. Another point, synchronous replication is hard to configure. You need to think about quorum, topology, commit timeout, and be prepared in your application code to all kinds of errors related to work with network. Final point is that synchronous replication doesn't support master-master topology. It's a limitation of the algorithm, not of the implementation. But on the bright side, you get higher data safety in case of master node failure. This is way more important than everything else sometimes. Now the practical part. Synchronous transactions in Tarantool before they are committed must be kept in memory to be able to roll back them in case of anything. In that place, the synchronous transactions must wait for replication confirmations, and when quorum is achieved, must be committed. Inside of Tarantool, there is a queue where the transactions wait. Since this is a queue, the first question is how to prevent its infinite growth. What if the quorum can't be achieved and new transactions come and come? For that, Tarantool provides a timeout configuration option, where you can specify how long each transaction must wait for its replication. And if it doesn't happen in time, it should back. The second option is the Synchro Quorum, via which you can control how many replicas should confirm a transaction before it is committed. Usually you want to set it to 50% plus 1, but you can lower it in case of some emergency, or increase or update when the cluster size changes. All that can be done dynamically, so it will affect the existing waiting transactions. To use the synchronous replication properly, it's necessary to understand that the synchronicity is a property of each individual transaction, not of the whole replication and not even of the entire instance. To make a transaction synchronous, you need to change a synchronous space. And to make a space synchronous, there is an option isSync, which you need to turn on for the spaces you want the synchro guarantees for. It's possible to do that for existing data in case you upgraded from an older version of Tarantool and want to use the feature. or set it for new spaces. Having it per space allows you not to pay for synchronous replication when you don't use it, or use it not often and not for all data. Here is a couple of examples demonstrating synchronous transactions. In one example, I change only synchronous space. Auto commit via a single replace is synchronous. A complex transaction having two changes also is synchronous. In another example, I change two spaces, one sync and one not sync, but the transaction still is synchronous, because one sync space in the transaction is enough to make the whole transaction synchronous. Here is an example of how synchronous replication works. I use a replica set with 3 nodes, one master and 2 replicas. In the config, I set a special option to turn off dirty reads. It costs some performance, but is needed to get all the synchro guarantees. Then I set the Synchro Quorum to 3, to 100% of the replica set. Here I used it to show some interesting cases in the example. In reality, as I said, you may want to set it to 2, as 50% plus 1. Then I grant all the access rights to the guest user so as not to care about them further. For the replicas, the configuration looks simpler. I don't need to specify synchro options on them. It's needed on master only. First thing, I create a synchronous space on master node. Then I insert something into it to show that while all nodes are alive, everything works. Then I kill one of the replicas. And now I start a new synchronous transaction in a separate fiber on the master node, so as not to block the console. I see that the fiber is suspended, so that transaction hang. I ensure that the transaction is not visible on the live nodes, because the quorum is not satisfied yet. I need quorum 3, and only 2 nodes are alive. Then I resurrect the killed replica with the same configuration, and I see that the fiber with the blocked transaction is finished. So the transaction must be finished too. I check it on all nodes, and indeed, the data is visible on all 3 nodes. Next topic directly related to synchronous replication is leader election. Normally, in a replica set, only one node is kept writable, so as to avoid conflicts, because if multiple nodes would be writable, they could try to change the same data and wouldn't know who is right. It is true even for asynchronous replication. In case of asynchronous replication, it's enough to set an option box COG read-only. When set to true, the node is read-only and is considered a replica. When it's false, the node is writable and therefore is a master. For master-master, the option is just false on all nodes. As for synchronous replication, things are a bit more complex here. Firstly, master-master is not possible. It's a limitation of the algorithm, as I mentioned earlier. Secondly, setting read-only option on an arbitrary alive node is not enough, because after a node leader dies, its latest committed transactions may be present not on all nodes, but only on a quorum of nodes. And there can be committed transactions whose commit entry the old master didn't manage to replicate. On replicas, they wait for leader decision, which won't be delivered if the leader is dead forever. It means there must be some special procedure for how to elect a new leader with synchronous replication safely, preserving the guarantees. Here is an example why an arbitrary node can't be elected. Here are 5 nodes. All of them store a value A equal to 10. Now a synchronous transaction changes it to 20. Manages to collect quorum of 3 nodes and be committed. The other 2 nodes didn't get the data yet. Now the leader dies. When elect a new leader, you shall use the nodes who participated in the latest quorum, so they have the latest data from the leader. If you elect any node with the old data, it will forcefully synchronize the other nodes and will delete all the newer committed data from them, so it can lead to data loss. To find the nodes having the newest changes, you can use vclock. In Tarantool, each transaction is identified by two values, replica ID and LSN. Replica ID is a unique identifier of the node who created the transaction. It is also called instance ID sometimes. LSN is a transaction ID, which is unique and monotonically growing inside the given replica ID. vclock is an array of these pairs, replica ID and LSN, showing essentially a snapshot of the entire cluster state at some point in time. Each node in the replica set stores the current known vclock and updates its own component in it. When nodes communicate, they compare their vclocks and can say who has the newest data in which component and what the nodes must download from each other. Consider an example on the slide with 3 master nodes having replica IDs 1, 2, and 3. vclock consists of 3 components as well. Now a transaction appears on node 1. The node 1 will update first part of the vclock and will send the transaction to the other nodes. It has replica ID and LSN1, so the other nodes will apply the transaction to the same vclock component. Now 2 transactions appear on node 2. It updates its own vclock component, second one. Then it sends the transactions to the other nodes with replica ID 2 and LSNs 1 and 2. The other nodes apply them in the same way to the same vclock component. By comparing vclocks on the nodes, you can tell which of them has the newest data compared to the others. For synchronous replication, you need to choose the node with the biggest vclock, at least in the old leader component. Then you guarantee that the new leader has all the committed data from the old leader. One way to do the election is manual, like it was with asynchronous replication, except that there is a new vital restriction on how to choose a new leader. To elect a new leader, you need to find the node with the biggest LSN in the old leaders component by looking at box info vclock on the live nodes. When the node is located, you need to finish all the pending synchronous transactions which it could receive from the old leader but which were not committed. They are still here in the queue of transactions. To finalize them, you need to call a function boxctl clear synchro queue. It will do all the work inside. You may want to prefer the manual leader election to automatic one if you already have all the election machinery working and you don't want to change it, and you are sure it's correct. Here is an example how it works. I use the same configuration as in the previous example about synchronous transactions, exactly the same. I create a synchronous space and check that it works. Then I kill one of the replicas, so as the next transaction wouldn't get the quorum. Then I start a new transaction of the leader, wait until it's replicated to the alive replica, and then I kill the leader. Then I restart the killed replica without the old leader in the config, because it's not needed anymore here. Then I check the transaction still is not committed. I don't see the changes. I want to elect a new leader, so I get the vclocks. They are equal, so I can make a new leader any of them. Note that the restarted replica also has this uncommitted transaction, even though it wasn't alive when the transaction was created, because after restart, it downloaded it from the alive replica. This is why the vclocks are equal. Firstly, I configure the synchro options of the new leader, because they were not configured before. Then I finalize the uncommitted transactions of the old leader, and now I can see the transaction is committed. Then I allow new transactions and demonstrate that they work. The manual election works. I can commit new transactions on the new leader. In Tarantool also is present automatic leader election. It does all the work for you, about finding the suitable new leader candidate and finishing the old transactions. Here is an algorithm of how it works. It's based on election via voting and collecting a majority of votes for the new leader. Each node can have one of the three roles: leader, replica, and candidate. All nodes start as replicas. Also, the entire lifetime of the cluster is divided into time intervals called terms. Terms are numerated, and the current term is stored on each node. They increase the term when start new election or when see a bigger term on some other node. Term numbers are used to filter out outdated messages from lagging nodes, so it works like a logical clock. The replicas expect the leader to send heartbeats. They have a timeout on when the leader is considered dead if it didn't send anything. The timed out nodes will start election. The timed out nodes become candidates, increase term number, and vote for self. Then they send vote requests to the other nodes. The non-candidate nodes will vote for whoever sent them a vote request first, but they will vote only for the nodes having newer or the same data, so as a node couldn't get majority of votes if it has too old data. In the end, either nobody is elected due to split vote and new election starts, or one node gets a majority of votes and becomes a leader. It sends a notification to other nodes that they should become replicas and start to follow. Now the leader is ready for new transactions. There are some options how to configure automatic election. First one is election mode. It allows to disable the automatic election at all, or choose which nodes can become a leader and which can only vote. You may want some nodes never become a leader if they are, for instance, physically too far. Second one is election timeout. It says how long each election round may continue at most before a new one is started. It is used to restart split vote elections. The last option is from Synchronous Replication, the quorum. It also regulates how many votes a node should get to become a leader. It is the same option used as Synchronous Replication because these two subsystems are tightly bound to each other in quorum size. Now I will repeat the manual election example, but with automatic election turned on. For that, on the master node, I set election mode candidate. Also, before granting access rights, I add box CTL waiter V, because right after box CFG, the master won't be writable until the other nodes will vote for him, so I wait. And when it's selected and becomes writable, and this function returns, and only then I do the rights update. On the replicas, I make them voters for now. I repeat the actions I did for the manual election. I create the schema, do one successful transaction, then I kill one of the replicas and start a hanging transaction, which is replicated to the live replica. Then the leader is killed. Now the master has no leader. I see that the transaction is not committed on the live replica. I make this replica a candidate and set quorum to 2, as the old leader will not return. After some time, I see the replica became a candidate when it sees that the old leader is dead and starts selection. Then I start the second replica again as a voter, so it would vote for the other replica. Now there are 2 alive nodes. One of them is a candidate, so the election should work. I wait for it via waiter V again. Now I see that the node became a fully functional leader. I see the transaction of the old leader is committed automatically, and I can create new transactions. Most of the actions here can be omitted if your nodes all start with read-only false, with election mode candidate, with proper quorums, and etc. Note that the read-only option, it still blocks new writes, even if the node is a leader. You need to be careful here if you use it together with automatic election. Both the considered features, synchronous replication and leader election, are based in Tarantool on Raft algorithm. It's well known, the most popular algorithm in this area, having some nice features. Firstly, it guarantees data safety while majority of nodes are alive. Secondly, it's extremely simple, so even a non-database programmer can understand it. Thirdly, it's well tested by time, and its correctness is formally proven. Fourthly, it comes with the automatic leader election out of box. The last big feature of Tarantool 2.6 is a new transaction manager. It's worth mentioning that we already had one, but for vinyl storage engine, which stores data on disk. We didn't have one for memtx engine, which stores data in the main memory with logs on disk. As a workaround for not having the manager, it was made impossible to yield inside memtx transactions, so as other fibers couldn't see the uncommitted data and do dirty reads. That made the transactions super fast, as they didn't need to care about read views, isolation, and other transaction manager stuff. There is an example on the slide on how a transaction could be aborted in case of a yield. This yield error made it impossible to use long-living transactions, so needed for synchronous replication and for transactions over network driven by a client. The critical point was the synchronous replication. Here is how dirty reads look when the transaction manager is turned off, so it's old behavior by default. In the example, I use the same configuration as for the first synchronous replication example, but with the only difference that I set the manager off. I create the schema, verify that the replication works, Replica, and create a hanging synchronous transaction. It can't be committed because quorum is free, but a live node count is just 2. And still I see the uncommitted data because the transaction manager is off, so all fibers see all data, even if it's not committed yet. If I turn the transaction manager on, like I did with the first example, the dirty reads will not happen. Here's an example not related to synchronous replication. How does it behave on a single instance? Because it can be useful here as well, the transaction manager. For the example, I use one node with the manager turned on and a single memtx space. Then I start a console to which I will connect from 2 terminals to try concurrent transactions interactively. I connect the terminals. Then I start a transaction in the terminal 1 to insert a tuple 1, 1. The second terminal doesn't see it. Now the first terminal commits the transaction. The second terminal sees the changes. A more complex example. Both terminals update data by the same key. Key 1. They increment the second field in the tuple by that key. First transaction is committed successfully in the first terminal. I see the changes. In the second terminal, the transaction fails due to a conflict because it relies on outdated data. It wanted to store 1.2, which would lead to the increment loss. So it was aborted as the transaction manager couldn't serialize it automatically. To demonstrate why does it matter if the transaction is reading, if it relies on the old data, I do a replace instead of an update, also by the same key 1. First transaction is committed successfully, and the second one is 2. Because it didn't read the old data, so it means it didn't rely on the old data, and it can't be broken, even if the data is changed before commit but after begin by some other transaction, so it works fine too. And here are some plans for future Tarantool versions. First of all the next releases will stabilize Synchronous Replication, Leader Election, and Transaction Manager, as they are still in beta. There is still a lot of work to do to make these features stable and reliable. Next, there will be a simpler way to configure Synchro and Election Quorum using a Lua expression on a number of instances in the cluster, which will be automatically recalculated each time when a replica is added or removed. For instance, instead of writing 3 for 5 replicas, 4 for 7 replicas, and so on, manually you will be able to assign the quorum to the quorum an expression half of n plus 1, where n is a number of replicas recalculated automatically, or any other expression on n. You won't need to update this option manually depending on cluster size. Next, there will be wider abilities to monitor synchronous replication, to check number of pending transactions, for example. Next, Tarantool will support transactions over network using our network protocol. Previously, to perform a multi-statement transaction, you always needed to implement it as a Lua function and call it via the network protocol. With interactive transactions, you will be able to use transactions in Tarantool without writing Lua scripts at all. Another useful coming feature, paired transaction options. You will be able to commit transactions in lazy mode, not blocking the current fiber. It would allow not to block the currently executing fiber until the transaction is finished. It will be especially useful for synchronous transactions, whose commit time may be long due to network latency. With lazy commit, you will not pay this latency, if for you it's not important to wait for transaction end. Also, according to the plans, you will be able to make any transaction synchronous, not only the ones which touched a synchronous space. For transaction on the whole, there are going to be options on what type of isolation level you want. Keep dirty reads for the sake of speed, or turn on snapshot isolation level like memtx transaction manager does now, or choose some other isolation type depending on your needs. Next, you will be able to install triggers on the node state changes when automatic election is working. You will be able to react on a node becoming a leader or a follower or a candidate immediately without polling. These features are the most interesting ones, but for sure there will be much more. Here are some useful links which you can follow to see more info and some more detailed talks on the subjects we talked about today.